Okay, let's go ahead and get started. All right. Wasn't quite ready today because I was trying to check something out, but let's go ahead and get started. So we're not going to be on the computer for long. I just wanted to show you the answers to the question for the day last time. So I suspect that we might get a different answer if we ask the older people. I think this could have something to do with the fact that young people tend to be more awake in the evening than in the morning. But anyway, it was an interesting question. So we are going to be on the document camera for today. So let me send that to the projector and let me be watching the same thing that you're watching. So we're beginning a new topic today that we're going to be covering for the entire week. We're going to be talking about what's known as recursion. Recursion is something that I would say is we think of as an alternative to iteration. Iteration is what we've been teaching you. Iteration is basically, writing loops, and it's kind of the basis of procedural style programming that we've been studying, particularly in the 142 class. So recursion is a different way of doing things. What I would say is that recursion and iteration are equally powerful. So you wouldn't want to have a programming language that didn't have either of them. You'd want to have something here. Recursion is more often used in a style of programming that's known as functional programming. Functional programming has an interesting status. I'd say most programmers are more procedurally oriented, but the functional programmers are very passionate. They're a minority, but they're a very passionate minority. And I think that what you find about recursion versus iteration is that we attach almost a religious aspect to it, or people have a devotion to recursion or iteration that's unusual. There's a story that people used to tell. I think it's probably not true, but I think it's interesting that people would think it could be true. That in the 1980s, the folks at MIT, who are very functional oriented, people who are teaching their intro course, wrote a textbook that taught functional programming, and it was almost all recursion. And the story is that on the first day of class, the instructors would ask people in the room, raise your hand if you've programmed before in high school. And these are MIT freshmen, almost everybody raised their hand. And the instructors supposedly said, I feel sorry for you, because you're going to find it more difficult to learn what we want to teach you than those of you who've learned nothing. So anyway, it's a kind of the idea that somehow learning iteration would in effect pollute your mind so that it would make it harder for you to learn recursion. This is an idea, as I said, I think it's probably not a true story, but I think it's interesting that we would consider the possibility that it's a true story. And I would say these functional folks have a kind of status that reminds me of the status that Buddhists have in the United States. They're a minority, they're not the most common religion, but they're a very passionate minority. So in any event, why study recursion? Well, there's a lot of reasons to study recursion. I mean, one of them is it's part of the culture, so that you want to be able to interact with Buddhists, so you want to be able to understand functional style programming. So we're going to want to teach you about recursion. It could be that you're a young Buddhist. It could be that you're going to find you really love all of this stuff, and that you kind of agree. Why did I have to learn this stuff? This stuff is a whole lot nicer. So who knows? Maybe you're going to like it more. But the real reason is that different problems that we come across in programming lend themselves better to either recursion or to iteration. So we want to have both of them available to us so that we can use iteration when it makes most sense to do that, and we can use recursion when it makes most sense to do that. So we kind of want to make sure that you have both available to you. And you may find this interesting, but every assignment we're going to do between now and the end of the quarter is going to involve recursion. So now that we've started doing recursion, we're going to do it for the rest of the quarter. So I like to do a couple of non-programming examples, and one of them requires people in the room, and I don't have people in the room. So, but I'd like to kind of talk about it. This is a diagram of Kane 120. This is me sitting in the front right here in Kane 120. There's the great big screen that we have that you actually can't see, but it's being recorded for you. So what I normally do is I normally kind of talk to somebody before the class begins, that I would talk to this person in this seat right here. And I would say, I'm going to ask you to help us out with something. I'm going to pick on you during the lecture, but don't worry, it won't be too awful. So normally I do that, and I ask people for their names. I didn't have the chance to do that this time. Oh, no, there's nobody sitting here. So what I did instead is I kind of put your names into a little program that randomizes, that shuffles. And I came up with some names. So I came up with Miles as the first name. So I'm going to pretend that Miles is sitting in this seat right here. And I'm going to ask Miles a question, which is, what row are you in? And I think actually Kane 120 is more clear. Some rooms aren't quite so clear, but I think this would be row 1, and row 2, and so forth. And if Miles were here, I think that we would see Miles solving the problem in a classic iterative way. That you'd see Miles. I mean, probably you guys are solving it in the same way. You're kind of looking down and saying things like, "Well, it's 1, 2, 3, 4." So I think of that as a classic iterative type solution. Start at the first row, start a counter at 1 while you haven't reached Miles, increment your counter and move back a row. So that would be a classic iterative style solution to this problem. So I usually challenge the class. I say, well, let's suppose that we aren't people, Miles can see 4 rows away. What if this was a room full of robots instead? So usually there's a crowd, there's lots of people here, and I say, is there a way to take advantage of the fact that we have a whole bunch of people in the room? And the analogy I'm going to use over and over again, so I'll use this terminology, is I like to think of them as robots. So when I'm thinking about recursive definitions, recursive solutions, I want to think about a bunch of robots who've been programmed with the same instructions to solve a problem. So suppose Miles is not a person with great vision who can see 4 rows away, but Miles is a robot. Maybe Miles has limited vision. He can't quite see that far away. But there's other robots in the room. Is there something that we could do that would allow Miles to ask another robot to help out? Is there some question that Miles could ask that would be a helpful question to ask? Let me begin with a bad answer to this question that I never get. People are smart enough to know that this isn't the right answer. But suppose that what Miles did is Miles asked some other robot in the room. So I've asked Miles, what row are you in? Miles doesn't know. So Miles turns to somebody else and says, do you know what row I'm in? And that robot says, no. But I'll ask another one, do you know? Do you know? Do you know? Do you know? We can ask every robot in the room. Anyone know what row Miles is in? No one knows, So that's a bad solution to this problem. So what would be a question that Miles could ask that would be helpful? And I get lots of interesting answers to this. I'll tell you the most common answer that I get to this, that's not a right answer, but it's an interesting answer, is people tell me to have Miles talk to the robot in front of him. And they say, why doesn't Miles ask this robot if this robot is in the front row? So that would be some useful information. So Miles knows he's not in the front row because he can see that, right? So he knows he's at least in row 2. And if he knew that this robot was not in the front row, he'd know that he's at least in row 3. So it's useful information. It gets closer to being done, but it's not really solving the problem. So, and I think one of the reasons that people ask a question like this is that in the iterative style of programming, we're used to having, say, Miles solve the entire problem himself. To have, what I want is cooperating robots, each of whom solve a little bit of the problem, rather than one robot who solves the entire problem. because that's the recursive way is going to be more to have a bunch of cooperating robots who manage to solve the problem together. And so, I ask different people, and I usually get somebody who says, well, Miles could kind of talk to the robot in front of him and say, what row are you in? So that's kind of the question that we'd like Miles to ask, is to ask the robot in front of him, what row are you in? Now, notice I asked Miles what row he's in. He asked the robot in front of him, what row are you in? So the question recurs. The same question is being asked of each, but Miles is asking a robot that's closer to the front of the room. So again, I did kind of this little shuffle before class began, and I came up with Dara as a second name. So Miles asks Dara what row Dara is in. And Dara says, not in the front row. So Dara asks the robot in front of her what row that robot is in. And again, the shuffle, I came up with Echo as another robot. So Dara asks Echo what row he is in, and Echo then asks this robot here, what row are you in? And the fourth name that I got when I did my little shuffle was Jenny. So suppose Jenny is sitting here. We assume that Jenny is not so blind that she can't tell that she's in the front row. So Jenny has a different way of solving the problem. So Miles, Dara, and Echo each ask the robot in front of them, what row are you in? But what Jenny does is Jenny says, oh no, I can see, I'm in the front row. I mean, I can see there's no robot in front of me. So Jenny knows that she's in row 1, and she gives that answer, row 1, to Echo. Echo then knows that he's in row 2. He tells Dara, Dara knows she's in row 3. She tells Miles, Miles knows he's in row 4, and Miles tells me. That's recursion. That's a recursive solution to this problem. Each of the robots doing a little bit of the work to put the overall task together, a solution to the overall problem. So that's kind of a good non-programming example to be thinking about. Let me put that aside. Another analogy that I like to use is I like to think about, suppose that you were asked to descend a staircase. So maybe you're up on top of this staircase right here, and you've been asked to kind of descend this staircase. So what I would claim is that if you have two things available to you, you can descend any height staircase. So if you have a way of going from your current step down a step, so if you have a way of kind of coming down one step, that's helpful. But you also have to be able to recognize when you get to the bottom of the staircase, when you reach here and you know to kind of stop descending the staircase. Well, these are what we refer to as the recursive case. It's recursive in the sense that I asked you to descend a staircase of a certain height, and you reduce it to another stair descending task that's simpler, because you will have gone down one step. It's like our robots that were dealing with simpler problems because each robot was asking a robot that was closer to the front row. So that was getting us closer to being done. That was kind of a reduction. This is what we refer to as the base case, sometimes simple case, same idea. So a base case or simple case. Let me tell you that every recursive solution that you're going to write is going to involve at least one recursive case and at least one base case. And I think you know what would happen if you were missing one or the other of these. If you're missing the recursive case, then the robot's kind of wandering around up here. How do I get down from this staircase? That's like me asking everybody in the room, do you know what row Miles is in? Do you know? Do you know? Do you know? Do you know? Nobody knows. We're not making any progress. So without the recursive case, we don't get closer to being done. We'd be in some kind of infinite recursion. And without the base case, this is like descending a staircase. I'm a clumsy person. I've actually done this often, where I've kind of miscalculated, and I think there's another step, and I kind of walk as if there's going to be a step, and I almost trip. So you don't want to be trying to descend a staircase when there isn't another step. So this is the case where we reached what we call the bottom of the recursion. This is what happened when we got to Jenny, is that Jenny dealt with things in a different way, that we reached a base case where Jenny was able to say right away, I'm in row 1. So these 3 were recursive cases where they asked somebody else a question. Jenny was a base case, just said, I'm in row 1, because Jenny could tell right away. All right, well, that's kind of some basic terminology. Let me say, by the way, also in terms of recursion, this is an interesting example of a topic where I could have done just 10 minutes today on recursion, kind of explain the concept to you and say, well, there's nothing more to explain, let's move on. Because in a way, that's true. Recursion doesn't have a lot of details associated with it. It's a relatively simple idea. But it turns out that recursion is not simple to master. It takes a while to learn how to use recursion well. So that's why we're going to spend all of this week talking about different kinds of recursive solutions. We're going to try to get you to a state where you recognize how to solve problems recursively. And then, of course, there'll be some homework assignments where we use it. So I want to start with a bit of code that is iterative. I want to kind of show you something that's more familiar, and we'll turn it into a recursive solution. So suppose that I had a public void method that I'll call write stars, and I'm thinking of a very simple thing here where you pass it an n, and it just has a loop that writes out n stars on a line. It produces one line of output that has n stars on that line. So, you know, chapter 2, we learned how to do for loops where you could say for int I starting at 1 or at 0, I less than n, I plus plus. Inside, we can do something like a system.out.print of a single star. So that can be inside of a loop. And then after the loop, we could do something like a system.out.println with the empty parens. Remember, you have to do that to complete the line of output. We do print, 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 print on the current line n different times, and then a println with the empty parens to complete the line of output. So that would be an iterative solution to this problem. What I'd like to do is to write a recursive solution to this problem. So we'd have a public void method called write stars that takes an integer n. So I mentioned that every recursive solution is going to have at least one base case and at least one recursive case. I hear different things from different students. Some people tell me that they need to think of the recursive case first. They need to see what kind of reduction is going to be going on before they can know where they're headed. I tend to think the other way, where I tend to think in terms of simple cases or base cases first. But, you know, you'll find out for yourself kind of what works better for you. But if I wanted to think here about base cases, one of the questions to ask, you know, there's different tasks to solve depending upon the value of n. What would be the simplest task, the simplest star writing task that we would be asked to do? What value of n? Sometimes people say 1. You know, writing a line of 1 star is pretty simple, but even simpler than writing a line of 1 star would be writing a line of 0 stars. So let me say if n is equal to 0, we're being asked to produce a line of 0 stars, and we can do that just by doing an empty println, system.out.println. That would be our base case, and we can say else we would do our recursive case. Now, there's a couple of things I think that are hard for people in learning recursion, and this is kind of partly validating that argument that I mentioned in that story about, you know, the MIT faculty saying that what you've learned already is going to interfere with learning new things. I think there's some truth to that, actually. So I think that what you're going to tend to think to do is to say, all right, if it's 0, you do the println else for int I equals 0, I less than n, I plus plus. You know, you tend to want to solve the entire problem. So that's your instinct, because that's the way we've been doing things. So one of the things that's going to be a challenge is learning how to do just a little bit of a problem, to nibble away at a problem. So in this case, what you know is if it's not an empty line of stars, you know that it's at least one star, then you know that no matter what, you're going to want to do a system.out.print of a single star. You know you're going to want to do that no matter what. The other thing that I think is very challenging for people with recursive solutions is something that we refer to as the leap of faith. I said that this is almost religious for people, that they have almost a religious devotion to these different things, to recursion or iteration and so forth. So one of the things that's hard is believing that recursion works. I've thought about, trying to do, pretend like I'm a preacher of some kind, believe in the power of recursion, make that leap of faith, and you'll find the homework easier to solve, and you'll get a higher score on the midterm. But it's actually true that if you can make the leap of faith, if you can believe that recursion works, you're going to be in a better position. All right, well, so if we believe that recursion works, look, so what did we do? We printed a star. So what if our n was 10? We were asked to produce a line of 10 stars, and we printed out 1 star. Then what's left to do? Well, what's left to do is to write out 9 stars and go to the beginning of a new line. In other words, to write a line of 9 stars is what's left to do. If only there were a method that would produce a line of stars, then I could call that method, if I believed it worked, I could call write stars passing it n-1. And then I would find that I'm done with this solution. Let me tilt this down a little bit so you can see the closed curly braces. I'd be done. Write stars of n-1, and then that completes the line. And that is, we are done. This completes the recursive solution. It doesn't seem right somehow, because you're writing the write stars method, so how come you can call the write stars method inside of the write stars method? Well, I mean, it's not magic. I mean, there are cases where it wouldn't work. Like, if suppose that I wrote this as a one-line method, where the way I do write stars of n is I just called write stars of n. Well, then what that would do is that would be the method calling itself over and over again. That would be like asking the room full of robots, do you know, do you know, do you know, do you know? And we're making no progress. So here the key reason why it's okay is that I'm passing n-1 on the call. I'm getting closer to an n of 0, which is just like what we were doing here, where we were asking a robot that was closer to the front of the room, an n-1 robot. Miles was in row 4, but Dara was in row 3. So we were kind of getting closer to being done. And that's why the leap of faith is justified in that case. Let me mention, let's just kind of do a simple example here, that what if I called write stars of 3, and I hope you'll allow me to abbreviate with just WS for write stars. So suppose I called write stars of 3. It's a lot like what happened if I asked, Miles, what row are you in? Miles would say, all right, his n is 3. That's not 0. So what does he do? He writes a star. Well, maybe I'll put the output over here. He writes out a star, and then he calls write stars of n-1. His n is 3, so he calls write stars of 2. That's like Miles asking Dara to pick up where he left off. So we ask Dara to solve the problem of write stars of 2. So Dara's n is 2. 2 is not 0, so we write out a star, and we call write stars of 1. So we bring up a third robot, like in our example, that would be Echo. We ask Echo to do write stars of 1. That n is 1, which is close to 0 but isn't 0. So we would write out a star and call write stars of 0. And this is like the case where we get to Jenny, in the front row. That if Jenny is dealing with the write stars of 0 task, she says, well, n is 0, and I'm told that when n is 0, I just do a println. I just complete the line of output, and then we're done. So this is where we bottom out in the recursion. We hit the base case. Jenny would do the println for us that completes the line of output, and we will have produced a line of 3 stars, just like we were asked to do. So 4 cooperating robots. Three of these robots are doing a recursive case, where they're printing a star and making an extra call. 1 robot is doing the base case, where they don't call another robot. That's where the recursion stops, and we kind of come back out of the recursion. I normally ask for questions, so I get some interesting questions. People will notice, for example, that if n is negative, then this does a weird thing. When n is negative, it ends up printing stars and calling on an n-1. This actually goes into an infinite kind of recursion. I mean, we could change this to if n is less than or equal to 0, and then the 2 methods would behave exactly the same. I think the better thing to do is to have some kind of exception code, that if they pass you a negative number, you throw an exception. Would be kind of the right thing to do in either of these cases. But that is true that the way I've written it, this has slightly different properties than the other one does. One of the things that I point out to people is that I think you've done enough iteration that you're used to things like, this is a line of code that's executed once before the loop begins. This test is controlling the loop, and over again, we're executing this, the update, executing this, the update, executing this, the update. There might be some code that we do once after the loop is done. So you're kind of used to a structure like that, how loops work. Well, this is actually a very typical structure of how recursive solutions are going to work, an if-else. And when there's more than 2 cases, a nested if-else typically, where we're distinguishing different base cases and different recursive cases. So case analysis is very important again, and it tends to lead to if-elses that are distinguishing different cases, different code to handle different kinds of cases. Okay, well, I want to do another problem with you where we kind of do it in more detail. I've had some instructors kind of say that students should make the leap of faith and they shouldn't have to be convinced that this actually works. But I find that students really want to be convinced, what are the mechanics of the recursion? Prove to me that this actually works. So I want to think about a problem. Suppose that we have an input file that has 4 lines of output in it. This is fun, no? So 4 lines of input in this file. What I want us to do is to write a method that's going to read the file and print the lines in reverse order. So no fun is this. That's kind of the output that should be produced by the method that we want to write. So we're going to write a public void method that I'm going to call reverse, that takes a scanner that I'll call input. Now, this isn't a hard problem to solve iteratively. What I would tend to do is to introduce a data structure that would store these lines so that I could kind of read them all in and then print them out in reverse order. I usually ask the class what would be a convenient data structure to use. I get different kinds of answers to that question. Sometimes people say an array. We've used arrays a lot, and so you've kind of gotten used to that. One of the problems with using an array is you don't know how many lines of input they're going to be. So an array list would be better, or a linked list. What I would say is even nicer, since you know that we're trying to do a reversing thing, this is a nice place to use a stack. So if we just kind of read this in and push it on the stack, push this on the stack, push this on the stack, push this on the stack, until there's nothing more to read, and then we pop, the stack, printing it in reverse order, then that would get us what we're looking for by using the stack. So that's not that hard. But it turns out that with recursion, we can solve it without a data structure that the method has to define. So we're gonna kind of let the recursion kind of replace the data structure for us in this case. So I've talked about the idea of the if-elses to distinguish different cases. So what's the simplest input file to reverse? I can get different answers. I always like it if somebody says a one-line file, because that's a good wrong answer. I mean, it's good in that a one-line file is easy to reverse, and you might think that's the simplest, but even simpler than a one-line input file is an empty input file. So kind of zero lines to the file is even easier to deal with. If there's an empty input file, there's nothing to do, because there's nothing to read and nothing to print in reverse order. So what I could do is I could say if it's an empty input file, and then have no code there, and then kind of an else. But that's a little weird, to have an if-else like that where the if has no code. So what I'm going to do instead, this is going to be a variation of the if-else that we saw a moment ago, is I'm going to say if it's not empty. So I'm going to kind of have the opposite test. If it's not empty, I'm going to say what to do, and there'll be an implied else there's nothing to do. Else it's a base case where there's nothing to do. So do you guys remember how scanners worked? We did it in 142. You can read entire lines of a scanner by making a call on a method called nextLine. How do you know whether there's a line to read? There was a method called hasNextLine. So I can say if input dot hasNextLine, if there is a line of input to read, then what I'll do is I'll read in that line. I'll say string line equals input dot next line. So I'll read in the line, and then what do we do next? Well, I want to mention a few things. I want to pause for a minute and mention a few different things. One thing is that I'm sure you've noticed that these recursive solutions are very short. It's one of the interesting things is that it can be very difficult to write recursive code, but often a very small number of lines of code can end up doing something very powerful. So it doesn't, in 142, or you think of linked lists, for example, we often had to write just tons of lines of code for all of the different details. Here it's the opposite. We often write very few lines of code, but they end up often solving a task in a very interesting way, doing something very complex. Well, so what that means is that that there may not be much more for me to write here in order to solve this problem. I find some students kind of seem to lean towards wanting to look at recursive solutions. They've heard about a problem, let me see the answer. They've heard about another problem, let me see the answer. So they do that a lot. I don't think that's helpful. I don't think that kind of looking at lots of recursive solutions is the way to learn how to do this. Because I think that you get to the point where you kind of recognize that a recursive solution works, but that doesn't help prepare you to be able to do to write a recursive solution on your own. So learning how to write recursive solutions is the hardest part. That's what you guys are going to struggle with most. And so I'm going to do what I can in the lecture examples to pause and try to let you kind of think about it for a minute. The other thing, too, that's a challenge is that we're going to have a range of where different people are at in terms of understanding a given recursive problem. It's quite likely that a third of you already see exactly what code I should write. So you'd be ready to, if you were here in the room, you'd be ready to call out the lines of code to write. And it could be the 2/3 of you have absolutely no clue what to do. Well, so what I would say is this is probably more of an issue for section because you aren't here in the room, so it's not going to be an issue here. But in section, don't just blurt out an answer. I mean, kind of wait a little bit and keep it to yourself. I mean, it would be great if you see how it's done, but kind of give your other classmates a chance to catch up, to kind of think about what their answer to this would be. So, because you might see right away, other people might need a little more time. Another thing that I would recommend, I'm going to try to give you just general advice about these things, but think about what this method is supposed to do. So often we're asking you to write a method that seems to be solving a very complex problem. And it's kind of like, how can I get it to solve that complex problem? But one of the things to recognize is that means that you get to assume, if you make the leap of faith, you get to assume that the recursive solution, that a recursive call does a lot of work, that it kind of takes care of a lot of the details for you. So one of the things to be thinking about is, all right, so suppose I've done a little bit. I've read the line of input. So that would mean that I've read in this string. What's left to do? So the input cursor would be positioned here. I'm not ready to print it out because I've got other lines of output to produce first. Well, what is there left to do? I'm supposed to read in these 3 lines of input and to print them in reverse order. So those 3 lines of input are supposed to turn into those 3 lines of output. This is a case where actually just writing down a description in English of what the method does can be useful to remind yourself of what the method does. Because think about it, once I've read in this line, then the next thing to do is to read these 3 lines of the input file and print them in reverse order. You're going to get sick and tired probably of this joke that I make over and over again, but I'm going to make the joke anyway. If only you had a method that would reverse a file, that would read in the lines of a file and print it in reverse order. If only you had such a method and you believed it worked, you could call it and believe that it does what it's supposed to do. Reverse the rest of the input, and then I should, if I make the leap of faith, I'll believe that it has read all 3 of those lines, printed them in reverse order, so the only thing left to do is for me to print this, to do a system.out.println of the line that I read in here. So I just kind of print that final line of the input, and then we're done. And remember, there was kind of an implied else there's nothing to do. So that's the complete recursive solution to this problem. Again, I think that people don't quite believe that these things work, so I'm going to try to convince you. So what we're going to do is we're going to do some very detailed tracing of what's happening here. Now, I think tracing is a useful skill to develop. It also makes for nice questions, very concrete kind of questions. Here's some code. What's the output when you make these calls? So this is what we're going to do in section tomorrow, is we're going to practice tracing problems. But I'm going to do this one with you. So what was my input file? Oh, right. It's got this 4 lines of input. This is fun. No. It's got 4 lines of input with the scanner positioned at the beginning of the first line, and we call up reverse. So what ends up happening? Reverse, executes. It says, does it have a next line? And it does. So it reads it in to its local variable called line. So it reads in the string this. And remember with a scanner that as you read lines of input, the scanner has its own little input cursor, its own little internal thing that keeps track of where it is in the file. So it'll remember that it's read in the first line and it's positioned at the beginning of the next line. So that's what happens when we execute this line of input, and then we get to a call on reverse. All right, if you've been asleep during the whole lecture or whatever, this is the moment to wake up. This is the most important thing from today's lecture. The most important thing to understand is what happens here. So I know some students who kind of think that somehow there's one version of reverse, and that when we call reverse here, it's like it goes back to the beginning. Like this is a go-to or something, and it goes back to the beginning. That is the wrong way of thinking of it. The right way of thinking about it is this way of thinking of it, is to think of it as a bunch of robots who've all been programmed with these instructions. There's an army of robots here. This is the right way of thinking of the reverse method, is that there's a whole army of robots that can each do the reverse task. There's as many of them as we need. We can call on as many of these robots as we need to solve this problem, and each of them is independent of the others. So we would make a call on reverse. So what does that do? That kind of brings us to here. We bring up a second robot. This is like Miles asking Dara to start solving a problem. So we bring up this second robot, and the second robot says, and this second robot is at the beginning of its execution, whereas this one is in the middle of its execution. This one has a value in its variable called line. This one hasn't even hit the line of code where the variable is introduced. So this robot is independent invocations. That's the really important thing to understand, is that there's a first robot and a second robot, and there'll be more robots, each of them independent of each other. So this one says, does the input have a next line? And it does. It's got a line that's got is on it. So it reads in that line. So it reads in the string is. Whenever you read in a line of the input file, the input cursor gets repositioned to the beginning of the next line. And then it calls reverse. Okay? So that was two of them. Now we've got a third one that's going to be involved in solving this problem. So now we've got a third robot that's at the beginning of its execution. Does the input have a next line? It does. It's a line that's got the text fun on it. So it reads in that text, fun. Input cursor gets repositioned. And then this one is now on this call on reverse. So we bring up yet another member of the reverse army. So now we have 1, 2, 3, 4 different robots working on this problem. This robot says, does the input have a next line? It does. It's that line that's got no on it. So it reads in that line. Input cursor gets positioned beyond there, which is the end of the file. There's just the 4 lines of input. And so, this robot could conceivably notice that we seem to be almost done, but it doesn't. It just kind of says, okay, we'll just keep going. It makes a call on reverse, and then we call up reverse. And this is like getting to Jenny in the front row, is that we have reverse. This robot says, does the input have a next line? The answer is no. It's kind of like, oh, well, if there's no line, then I just exit the method. I'm done. So this one is the base case. This is where it stops. We bottom out. It's like reaching the front row with Jenny. We stop. So this is where the recursion stops. I wanted to mention one idea. I'm kind of showing you a visual representation here of something that's worth knowing about, the technical term for it. How would you describe it in English? I have a piece of paper, and then another one here on top of it, another one on top of that, another one on top of that, another on top of that. Wouldn't you call that a stack of papers? Isn't it a stack? And what I'm showing you here is a visual representation of what we refer to as the call stack. So it's a visual representation of what we know of, what we refer to as the call stack. You've seen the call stack. When an exception is thrown, you get a series of lines of output that show you the call stack in reverse order. You are in line such and such of this method, which was called from line such and such of this method, which was called from line such and such of this method. That's the call stack. So here the call stack has 5 things because we've made 5 different calls. But we got to the base case where it says, okay, there's nothing left to do, and this one is done. And what happens when methods are done executing? They go away. So we tear it up, pop the stack, and we come back to where we were before. Well, where were we before? We were in this call on reverse. So now that's done. So this one does a println of its text, which is no with a question mark. And then it finishes executing. And what happens when methods finish executing? They go away. We rip it up and we pop the stack and it goes away. And we come back to where we were before. There was this call on reverse. Now it's done. So we're going to do the println of fun, and that's going to, and then this method finishes executing. It's done running. So we tear it up, pop the stack, and it's done. We come back here where we finish this call on reverse. We now print out our text, which is, and then it finishes executing, and so it goes away. We pop the stack, and we come back to where we were originally. We've done a whole lot of work in this call on reverse, but it's done now. It's done all of that work. That would be like Miles waiting for all the other robots to kind of talk to each other to figure out what rows they're in, and then it finally comes back to him, and he gets to finish this whole thing out. Notice that the leap of faith was justified in that these 3 lines of output were read in and printed in reverse order. We did, in effect, use a stack. We used the call stack. We weren't using a stack that was a local variable. We let, the recursion takes advantage of the call stack is basically what we did instead. And so now this one finishes out the overall thing by printing out this, and then it's done. And it's like Miles telling me he's in row 4, and then it's done, and the overall thing is done. Okay, so that's kind of a detailed examination, a detailed trace of what's happening when that call is made. And you're going to practice tracing. I think it's useful for you to understand these mechanics of recursion in order to better understand how to write recursive solutions. Thursday's section is going to involve learning how to write recursive solutions. We're going to talk to you in the lectures about how to do some of these things as well. All right, I have time to do one more example with you. I want to talk about a method that I refer to as Stutter, that if you had a number like 348, I want it to return something that replaces every digit with 2 of that digit. So 334488. So it has a stuttering effect of getting us, kind of the multiple digits there, 334488. So I want us to think about how to write this method. So we're going to have a public int method called Stutter that takes an integer n as a parameter. So what would be the easiest number to stutter? And, I've given you 2 different examples where the easy answer was 0, and you might be inclined to say 0. 0 is actually a funny case because there isn't really a 0, 0. So how do you stutter 0? We would just say by definition that if you're given 0, that gets turned into 0. But if you think about it, what are the easy cases to stutter? People usually are pretty good at figuring out that it's 1-digit numbers, that a 4 gets turned into 44. So 1-digit numbers are pretty easy to do. And how do you do that? Well, when I thought about it initially, I remember thinking to myself that I kind of want a 40 and a 4, so kind of 10 of the n and an extra n. That's 11 of those n. So you guys might have seen that just right away. That I don't know if you did times tables when you were a kid. I did. 5 times 11 is 55. So I don't know whether you had to memorize things like that. But multiplying by 11 is helpful for 1-digit numbers. I'm going to add to this for right now a precondition that n is greater than or equal to 0. I don't want to think about negative numbers just yet. So I'm going to say if n is less than 10, that would be a 1-digit number, then what I'm going to return is n times 11. That's my base case. I'm not doing any recursion there. That's going to be my base case. And else, what am I going to return? Well, otherwise, I have something like an n that's 348. That's a 3-digit number. So how can I get a 3-digit number closer to being a 1-digit number? We've talked about how to break up numbers like this. How do we get the final digit of a number like that? N mod 10 gets you the final digit. And how do you get the leading digits? N divided by 10 gets you the leading digits. Well, so these are numbers that have fewer digits than the original. And so leap of faith would be appropriate here. If I think about what happens if I stuttered this, that would give me back an 88. What happens if I stuttered this? If it works, it should give me a 3344. Can I just take these 2 things, 3344 and 88, and add them together like that? No. I want 3344. And I kind of want to scooch it over, right? Don't I want a couple of zeros there? How do I scooch this over so that when I add, it's going to do the right thing? And people usually say you multiply it by 100. Well, you may not realize it, but that's actually the entire solution. We are going to return what you get by taking 100 times what you get when you stutter n divided by 10, and you add in what you get by stuttering n mod 10. That's just me rewriting the different pieces that we had here. We take the stutter of n mod 10 and add it to what we get by stuttering n/10 and multiplying that by 100 to scooch it over. So that's kind of the whole solution to the problem. I'm going to have a numbered handout from today, in case you're interested, that has all of these examples. This is what I put on that handout. I dealt with the negative case as well. When n is less than 0, I return minus stutter of minus n. That's an extra recursive case, so that deals with the negatives. I do try to draw diagrams. You know, it's hard to understand these diagrams, but I do the best I can to kind of diagram how a certain call is worked out. The TAs will give you their own ways of seeing this and drawing pictures of it. But if you're interested, there's that numbered handout. It's on the web page already under the Handouts tab if you're interested. And we'll do more.